Here we are. So session 2A, so we're talking about visualizing environmental factors. My name is Justin Clarke. I work for the Federal Highway Administration on highway performance monitoring system is kind of our bread and butter. I work in the Office of Policy at the Federal Highway Administration. So this next session is talking about the interaction of weather and environmental factors on transportation and then the visualization thereof. So we have some interesting presentations, and we're going to start off with Shuo Wang, who is a PhD student at Iowa State University, specializing in transportation, big data analysis, and machine learning. He's been working on projects related to large-scale traffic and weather monitoring for Iowa DOT since 2015. Okay.
Good afternoon, everyone. My name is Shuo Wang from Iowa State University. Today, I'm going to present visualizing the statewide impact of weather on interstate traffic operations. So as everybody knows, weather has been identified as a significant impact factor on traffic in various studies. So in this presentation, I'm just going to show you a case study in Iowa where we focus on providing a systematic visualization using big data techniques to visualize the impact of weather on a statewide traffic. So a product from this study is a time-lapse video, which can show how the traffic changes throughout the day or a certain period you selected. And on top of it, we overlap the weather factors to see the impact and on how the speed evolves. And the figure on the right is a snapshot of one of the videos. So here we use two different data sources to provide this product. So the first is a high-resolution real-time statewide weather data. So those weather data are collected from both our VIZ system, which is Road Weather Information System, and National Weather Service system. And we also have real-time traffic flow data. So those traffic flow data are collected both from radar sensors and the commercial probe data, which is INRIX. So all of the data, those data provider just provide us a data portal link, which is a URL. So the data comes in a streaming fashion. Those URL will refresh in a certain time period. So we need to build up a system which can record those data, establish a big data set, which can accommodate this large size of data and provide fast processing speed. So first is the description of the weather information we are collecting. So first is the weather information is a high resolution. So the figure on the right is a map of Iowa. So we collected weather from this rectangular, from the very west to the very east longitude and very south to the very north latitude. And we divided those area of interest into small grids. So each grid is a small square, which is 0.01 degree of latitude by 0.01 degree of longitude. So the entire interest of area, which is Iowa, has been divided into 660 by 324 small grids. So we collected weather information. We collect 11 different weather information from each grid. So those 11 features, including temperature, dew point temperature, road surface temperature, wind speed, wind direction, precipitation, radiation, and snow depths, and more. As you can see, we have a statewide coverage. And the traffic information we collect both from radar sensors and probe data. So Iowa DOT have invested 400 plus radar sensors statewide. And the data comes in streaming fashion every 20 seconds. And the commercial probe data are provided by INRIX. It provides a larger coverage than radar sensors. It also comes in a streaming fashion by every 1 minute interval. And this study, because we analyze the impact of weather on traffic on a statewide scale, so we use the commercial probe data more than radar sensor. So radar sensor will be a complementary to the probe data. So to accommodate those data, we have some challenges, and most of the challenges come from the big size of the data. So those weather data the data comes in from those grids every 5 minutes. So one screenshot of the weather information is 36 megabyte. So we have 36 megabyte per 5 minutes of the weather information, which grew into 3.7 terabytes per year. And Vivotronics, we have 2,100 gigabyte per year. Inrix, we have 20 terabyte per year. So as a total, we need a storage which can accommodate 6 terabytes per year data. And our storage need to provide enough storage and the security and the easy access. And also, more importantly, the data cannot just sitting there. So after you store, archive all the data there, you have to be able to process it. So for example, one day one person comes in and asks you, can you provide me the average speed of, annual average speed of the last 5 years of a certain segment? We should be able to provide that. And the next day, another person comes in, can you provide the hourly average speed, hourly average weather of last 3 months of another 5 segments? We should also be able to do that. So to overcome those challenges, we using some big data techniques to build up our system. So first of all, we use the Hadoop distributed file system, which is HDFS for short. So it can provide large storage. So HDFS is physically just a collection of a lot of computers. So our currently major cluster have 14 machines there, so 42 terabyte storage in total, and this system can be easily expanded to more and more machines. And it can provide reliable storage, so all the data you throw in there, big data you throw in there, will be chopped into small pieces, and those pieces will be located into different machines, and each pieces will be made to 3 copies. Each copy will be stored in different machines. So if one machine goes down, you won't lose the file. And also all the metadata will be stored somewhere in the system. System handle all the low-level things. So when you use the system, you won't actually notice the file are stored distributedly. And another major advantage of this, it can run MapReduce on top of it, which is a parallel processing algorithm. So it can process the big data sets much faster than the regular methods. So for example, if you want to find the maximum, easy task is you want to find the maximum precipitation of this large data. So instead of just going to find the largest value, you assign the task to each machine. So each machine, you only in charge of finding the largest value of this group of data. You only in charge of finding maximum value for this group of data. Then after everybody done their job, so summary and provide you the maximum value of the entire data set. So that's the parallel processing. And so of course, the current parallel processing have a lot of limitations, but in our tasks, we need to do a lot of filtering, grouping, and aggregating to process the speed and weather, and MapReduce are just good for them. Okay, so the big size of data, most of them, like 60% of them is contributed by the weather data. So we want to find a way to limit its size because as I said before, it's 6 terabytes per year, but we only have 42 terabytes of system. And because we make 3 duplicates to make the system reliable, so the actual usable storage is only 14 terabytes. So we need to find a way to reduce the weather data. So because the weather data comes from the snapshots of the rectangular area of interest, so it looks very like an image. So we think we can convert the weather information into images. So eventually we convert the weather into PNGs. So if you view PNG as images, so the 3 different channels are red, green, blue. But if you just view the PNG as a general format of how you store area-like data, so the first channel can be a precipitation channel. The second channel can be your temperature channel. Third channel can be your wind speed channel. So you can store your weather information into those image-like PNGs. So because our area of interest cover entire Iowa have a 660 by 324 So the PNG will have the similar amount of pixels. Each pixel of each channel represents the value of that location. So by converting weather to PNGs, so before I have 36 megabyte per snapshot of weather information, now we have only 4 kilobytes per PNG. And so this is the entire pipeline, how we achieve this data transition. This transition is totally done by parallel processing. So from eventually we have 3.7 terabyte per year, it goes down to only 2.5 gigabyte per year of the weather. Of course, you lose some resolution in weather, because to convert to PNG, you have to bin those values. So you cannot have the continuous values. You need to convert the value to 0 to 225. You lose some value, but you won't lose the most information in the weather data. And the processing speed of this, it takes time. So this process takes about 5 to 6 hours to process 1 month of data, but you only need to do it once. So once you have converted all the weather into PNGs, those PNGs stored in the distributed file system, which will be ready for you to query very fast. And after we have the converted PNG, we can write a parallel processing query program to directly generate a video, time-lapse video for you. So for example, to generate this time-lapse video, which is shows you the precipitation of July 31st of 2016. So to generate this video, in our program, you only need to input the date, and it will take like a minute to create the video for you. And so this is a way to visualize the weather statewide. So to visualize the impact of weather on traffic, we also want to overlay traffic information on this weather information. So we can do the similar processing to traffic, but in order to overlay them together and to provide informative visualization, so we decide to use a 3D plot. So on those two figures on the left are showing the snowfalls of a certain day. So on the very left is the raw data of the snowfall. So it's not smooth. After the smoothing, it looks in the middle. And on the right, it shows the traffic slowdowns. So those red bars, the height of the red bar represent the difference between the current speed and the reference speed, which is a speed limit we used. So each red bar represents you have a current traffic speed lower than reference speed, and the height of the bar represents the severity of the congestion. So if we overlay them together, so we can have a product like this. Then from our system, we can easily create a video like this to show the impact of snowstorm on traffic. So on the left is a snowstorm day, which is November 20th of 2015. On the right is November 13th, 2015, which is a normal day without snowstorm. Both of them are Fridays. So this is a time lapse from midnight in the morning and to the end of the day. So you can see in the afternoon, the snowstorm rolls in and the traffic slowdowns start to grow up. And right in the middle is the Des Moines area of Iowa, if you are not familiar. So currently, this is just a demonstration video. So from our big data enabled Hadoop system, we can easily to create those videos. So our next step will be to create a API for users, which website-based API. So users from, for example, Iowa DOT, they can submit a request to generate a video of a certain day, of a certain area, or the entire state, and the system should be able to return a video in a very short time. And Thank you. Any questions?